On the last day of 2019, fires in southeastern Australia built something far larger than a smoke plume. They built thunderstorms. Heated columns carried smoke across the Tropopause, the stable boundary containing almost all ordinary weather. Then, part of that smoke began to rotate. Solar heating produced a self-maintaining vortex roughly 1,000 kilometers across. It lasted more than 13 weeks, traveled about 66,000 kilometers, and lifted smoke as high as 35 kilometers. This was a coupled fire, cloud, and atmospheric engine, a pyrocumulonimbus storm, usually shortened to pyroCb. To understand it, we must follow the energy from the flames all the way into the stratosphere. A normal cumulonimbus begins when the atmosphere supplies buoyant, moisture-bearing air and some trigger lifts it far enough for deep convection to take over. A pyroCb changes the trigger. The heat and moisture source is an intense fire. But an intense fire does not automatically create a thunderstorm. This is the threshold we need to explain. Most wildfire smoke rises as a turbulent plume, then spreads sideways when mixing, or a stable layer removes its buoyancy. A stronger plume may cool to saturation and grow a small white cap called pyrocumulus. It is a fire-generated cloud, but not yet a thunderstorm. Only when the column remains buoyant through a deep layer does the third outcome appear, a glaciated tower, an anvil, and often lightning. That is pyroCb. So the real question is not whether hot air rises, it is whether a smoke-filled column can survive dilution long enough for cloud physics to take over. At the base of the plume, the fire heats the air and adds water vapor and smoke. The mixture expands, becomes lighter than the surrounding air, and begins to rise, like the warm air above a heater, but on a far larger scale. Whether it keeps rising depends on a tug of war. On one side is upward lift from the fire's heat. On the other is cooler surrounding air being mixed into the plume. That mixing happens along the ragged edges of the rising column. Scientists call it entrainment. It makes the plume larger, but it also dilutes its heat and moisture, so the upward lift becomes weaker. Wind can tilt the column and increase mixing. Dry air can cool it as moisture evaporates. A stable layer can resist the climb, rather like an atmospheric speed bump. If the fire-driven lift stays stronger, the column keeps rising. If cooling and mixing win, the plume bends over and spreads sideways. That balance is the important idea. We do not need to calculate it. We only need to see which side of the tug-of-war is winning. The next question is simple. How much firepower is enough? Researchers call this the firepower threshold. It is not one fixed number for every wildfire because the atmosphere sets the hurdle. Imagine that the plume must climb high enough to reach moist air, where cloud formation can begin adding extra energy. If that supportive layer starts low, the climb is shorter and the fire needs less power. If dry or stable air pushes the target much higher, the fire must do far more work before cloud physics can take over. Height matters especially strongly. As a useful rule of thumb, doubling the required climb can raise the necessary firepower by roughly 4 times if the other conditions remain similar. So, two fires that look alike at ground level can produce very different skies. The atmosphere decides how high the hurdle is. The fire must supply enough power to clear it. As the plume rises, pressure falls. The air expands and cools. If it reaches saturation, water begins condensing onto airborne particles, including particles in the smoke. Now the energy pathway changes. Condensation releases latent heat. Higher in the cloud, freezing releases more. Those phase changes partly offset expansion cooling, helping the rising mixture remain warmer than its surroundings. The cloud can now draw energy from atmospheric moisture as well as from the fire below. Smoke also modifies the cloud's microphysics. A large population of aerosol particles can produce many small droplets competing for the available water. Small droplets collide and merge less efficiently, which can delay warm rain. Strong updrafts may then carry more liquid water above the freezing level, increasing ice production and latent heating aloft. But this effect is conditional, not automatic. If the environment is too dry, evaporation can weaken the column. If the plume is too diluted, no amount of smoke particles will create deep convection. Heat flux, moisture, stability, wind and aerosol loading work together. None is a universal switch. In the mixed phase region, supercooled droplets, small ice crystals and graupel occupy the same turbulent volume. Graupel is soft hail, ice particles coated by freezing droplets. When ice crystals rebound from graupel in the presence of supercooled water, charge can transfer between them. The light crystals are carried upward more easily, while the heavier graupel follows a different path. Their separation builds an electric field until the air breaks down and lightning discharges. Smoke and ash can be electrically charged near the fire, but the intense lightning inside a mature pyroCb is fundamentally thunderstorm electrification, driven by mixed-phase ice physics. During the 2021 Sparks Lake pyroCb in British Columbia, researchers recorded more than 5,600 lightning strikes in 5 hours. Some flashes remain inside the cloud. Others reach the ground beyond the fire and can start new ignitions. The tropopause is often drawn as a line, but it is not a physical lid. It marks a sharp change in stability. Through most of the troposphere, temperature generally decreases with height. Near the tropopause, that decrease stops, and the lower stratosphere becomes much more resistant to vertical motion. A rising parcel entering this environment loses buoyancy and should slow. Yet a powerful updraft has momentum. It can overshoot its level of neutral buoyancy, producing a dome above the flattened anvil. In the strongest pyroCb storms, the updraft carries smoke, water vapor, and ice through that overshooting region and into the lower stratosphere. Some material mixes back into the upper troposphere. Some ice falls out. A pyroCb, therefore, does not permanently puncture the tropopause, and not every overshooting top leaves a lasting stratospheric plume. But material that remains above the tropopause enters air with very little precipitation and slow removal. A deep convective column can move surface emissions through kilometers of atmosphere in well under an hour. That is the moment a local wildfire acquires a hemispheric pathway. The Australian outbreak shows what can happen after injection. The initial storms placed smoke near the lower stratosphere. Then black carbon and dark organic particles absorbed sunlight and warmed the surrounding air. Under the right conditions, that heating made the smoke-bearing layer rise gradually, a process called radiative self-lofting. The most concentrated smoke patch also developed an anticyclonic circulation. This was not a gigantic fire tornado. It was a broad pressure and wind anomaly organized around a heated smoke bubble in the stratosphere. Satellite instruments and atmospheric analyses followed the structure for more than 13 weeks. It traveled about 66,000 kilometers while the smoke bubble climbed toward 35 kilometers. The sequence matters. First, deep convection injected the smoke. Later, sunlight heated it. The vortex helped confine it, and the combined structure ascended. The fire did not blast smoke directly from the ground to 35 kilometers in one continuous jet. Australia is the case study, but the mechanism is not uniquely Australian. PyroCb storms have been observed over boreal forests in Canada and Siberia, as well as temperate forests in Australia and elsewhere. What they share is not one fuel type or one continent. They require a sufficiently powerful, coherent fire, an atmospheric profile that lets the plume reach saturation, enough moisture for deep mixed-phase cloud, and winds that do not destroy the column before convection becomes self-sustaining. Once established, the storm can feed back on the fire below. The rising column draws air inward near the surface. Evaporation and precipitation can create downdrafts that spread outward when they reach the ground. Those flows may shift wind direction, transport embers across control lines, and complicate fire behavior. Lightning can extend the ignition pattern even farther. So, pyroCb is not merely smoke traveling upward. It is two-way coupling. The fire reorganizes the atmosphere, and the resulting storm can reorganize the fire environment. The ladder from wildfire to stratosphere now has 4 distinct energy transfers. Combustion heats and moistens the plume. Buoyancy converts that heat into vertical motion. Condensation and freezing release latent heat, allowing deep convection and lightning. If the updraft overshoots the tropopause, sunlight can later heat the injected smoke and lift it still higher. Break any major link, reduce the firepower, increase entrainment, strengthen the cap or remove the moisture, and the outcome may stop at an ordinary plume or a shallow pyrocumulus cloud. A pyroCb is therefore not simply a very large wildfire, and it is not a cloud made of flame. It is a thunderstorm whose trigger and lower boundary are supplied by combustion. Australia's Black Summer revealed the full reach of that engine. Energy released by burning vegetation reorganized a cloud, crossed an atmospheric stability barrier, and left smoke circulating far above ordinary weather for months. The fire did not defeat the atmosphere. For a brief and dangerous interval, it became part of the atmosphere's machinery.